Yes, good morning, my dear students, and welcome to Vijay's online classes. Look here, in the last class, you are discussing about the types of semiconductor. Especially, you are discussing about the intrinsic semiconductor. You are discussing about the intrinsic semiconductor. As we know, in broad, we can classify the two types of semiconductor. One is called intrinsic, another is extrinsic semiconductor. And maybe you completed about the intrinsic semiconductor, and today go for the extrinsic semiconductor. As usual, before going for the today's class, we go for what you studied in the last class. We can regain or refresh your knowledge. And today going for the lecture number 4. Today we are going for the lecture number 4. Look here, as we know in your intrinsic semiconductor, the important thing we discussed in the last class about the effect of the temperature on your intrinsic semiconductor. We studied in the last class the effect of the temperature on your intrinsic semiconductor. As we know already, for the lower temperature, your intrinsic semiconductor that acts as insulator. For the lower temperature, your intrinsic semiconductor that acts as a insulator. Why? Because as we know already, you seen in the last class, according to the energy band diagram, this your valence band, conduction band, and this your valence band, and here your energy. Important thing we know about Eg, that is about for your point added here. For germanium it is 0.3 electron volt, and for silica it is 0.7 electron volt. Or in general 1.1 electron volt for in general semiconductors. It means in intrinsic semiconductor for low temperature, why it acts as insulator? Because no doubt you are applying the temperature. The temperature is very low, and you are applying the low temperature. Because of the temperature is some energy. Because that energy is not sufficient, it is not more than 1.1 electron volt. That's why whatever the valence electrons are there in the valence band, they are not moving towards the conduction band. That's why your intrinsic semiconductor acts as a insulator low temperature. Why the intrinsic semiconductor acts as a insulator low temperature? Because you are applying the very less temperature. Because less temperature, nothing but less energy, and that less energy is not sufficient. It is not more than 1.1 or it is not more than 0.3 or 0.7. That's why what happens? The valence electron, they are not moving from valence band to conduction band. They are tightly bound to the parent atom. That's why you are not having any current conduction in the low temperature. That's why it acts as insulator for low temperature. And what about high temperature? What about high temperature? What about the high temperature? What about the high temperature? Look here, for high temperature, you are applying high temperature because you have nothing but you are applying with high energy. That energy is more than 1.1 electron volt or more than 0.3, more than 0.7. That's why the valence electron they easily can move from the valence band conduction. That's why I have more current in the high temperature. Why you are having more current high? Why you are having more current high temperature? Because you are applying the energy here. Because of the you are applying high temperature. Because high temperature you are having high energy. That energy is more than 1.1 electron volt or it is more than 0.3 or 0.7. That's why the valence electron can easily move from the valence band to conduction band. That's why it conducts. It acts as a conductor for the high temperature. Or what I said on the way, no doubt here I am the valence electron in the valence band. And if you are applying the energy, then what happens? You are breaking the covalent bond. You are breaking the, because of more energy, and at energy more than 1.10 electron volt, then you are breaking the covalent bond. Whenever you break the covalent bond, what happens? The valence electron, they move towards a conduction band. The valence electron, they move towards a conduction band. It means you are breaking the covalent bond, then what happens? Because you are applying the high energy. Because high energy, they can break the covalent bond, and whenever you are breaking the covalent bond, no doubt, the valence electron, they move towards the conduction band. And here you are having the electron. And this, we can place the position nothing but hole. It means, as I said in last class, whenever breaking the covalent bond, no doubt, the electron hole will come in pairs or generating pairs. How many you are breaking the covalent bonds, how many number of you are breaking covalent bonds, that much of the electron will come in pairs. It means you are applying the high energy, you are high temperature, because you are breaking the covalent bond, no doubt, the valence electron, they move towards the conduction band. It means that we can place a position nothing but the hole. Here, this electron, they move towards here, they will create a hole. Then, this electron having the energy, they will break the covalent bond, they move towards here. Here, it create a hole. And here also, like that, they create another hole here. It means how many numbers polar you are breaking, that number of electrons are generated, also the same time holes are generated. And it means the important thing in the semiconductor, we can break the covalent bond by applying the high temperature. Then only the valence electron, they can move towards the valence band conduction band. And also, you discussed in the last class about the total current, I is equal to IE plus IH. No doubt, in the semiconductor only, the current is because of electron and because of holes. In general, in conductors, the current is because of only electrons. But in semiconductor, the current is because of electrons as well as the current is because of the holes. And as you know, this conduction electron, they move towards the positive side. It means the moving of electrons from valence band to conduction band, and that is nothing but the free electron, they move towards the current because of the free electron, nothing but the electron current. The current because of free electron, that electron move towards the positive side, that current nothing but the IE. And what about IH? What about the whole current? As I said, the important thing here, this whole one electron, they move towards the conduction, but here they will create a hole, right? And because it will create a hole, and property of hole, I said in last class, it attracts the neighboring electrons. The hole having the positive charge, the property of hole is nothing but they will attract the neighboring electrons. And it means here electron is there. This electron is there. This electron will be attracted to this hole. This electron will attract to this hole. And here, now your hole will disappear. But here, we will create a hole. And this, once again, here having some electron. This hole is there. Once again, this hole, what they will do? They will attract the neighboring electron. Then, here, this is completed. Then, this is completed the bond. Then, it becomes here hole. Like that, the holes are moving in the valence band in the opposite direction to the electron movement. The holes are moving in the opposite direction to the electron movement. And yesterday, in last class, I said how to remember the moving of holes. It is very simple, as similar to your playing Coco. The playing Coco is a very good example to understanding about the whole current. And this is about the importance about your how actually the current conduction is in your semiconductor. Or for example, maybe I said in the last class, this is your semiconductor, and if you are applying the voltage to the semiconductor, no doubt you are having the electrons also there, and also the holes are there. No doubt they are in the same numbers, because that is the breaking the covalent bonds to get the electron will come pairs. And as we know, this electron, they move towards the positive side. This is nothing but movement of electron, and this is nothing but movement of hole. Always the holes move towards the negative side and the electron move towards the positive side. This movement of electron hole nothing but the electron current and hole current. This much you studied in the last class. And Navi Copper, Another important thing in the before that we go for the what are the drawbacks or your disadvantages of your entrance semiconductor. What are the disadvantages? What are the disadvantages? What are the disadvantages of entrance semiconductor? Of intrinsic semiconductor. Why you are not preferring the entrance semiconductor? Why you are not giving importance to the entrance semiconductor? One thing important here, now we discussed the most important thing, drawback or limitations or disadvantage of your entrance semiconductor. That is something but it acts as a insulator for low temperature. And next, the important thing, the number of holes equal to number of electrons. This is also one drawback of your entrance semiconductor. Number of holes and number of electrons same, because I said whenever breaking the current bond, no doubt the electron and hole they come in pairs, they generate in pairs. And last one about the conductivity is very less. The conductivity is very less. These are the important limitations or drawbacks of your entrance semiconductor. Why you are not preferring the entrance semiconductor? Because it acts as the insulator for your lower temperature, and number of holes and electrons same, and also conductivity very less for your entrance semiconductor. That's why you are not giving importance to the entrance semiconductor. Now we go for the external semiconductor, and before that we will go one small thing is that is important. And before going for the external semiconductor, you go for that. That is something about recombination of electron and hole. What is the recombination of electron and hole? It is so important process in the semiconductor. Look here, as I said, if you are not applying any external voltage, then what happens? Electrons and holes, they will move in a random motion. If you are not applying any external voltage or battery, you are not applying any DC voltage, then what happens? How union conductors, also you are not applying any external voltage. No doubt electrons are moving, they are moving in random direction. If they are moving in random direction, you are not having any current. The same way for semiconductors, if you are not applying any external voltage, then what happens? The electrons and holes will move randomly. Whenever they are moving randomly, what happens? Some of the electron will recombine. They will coincide. They will recombine. Then what happens? They will disappear. And they will neutralize. And they will give some energy. Because that energy can once again break the covalent bond. That is something but recombination of electron hole. It means whenever you are not applying any external voltage, the electrons and holes are moving, no doubt. Also, some of the valent electron or some of the holes, they will recombine. Some of the electrons and holes recombine. And whenever they recombine, what happens? They will neutralize, they will disappear, and they will give some energy. Because that energy will again break the covalent bond. That is nothing but the recombination process. Or another way also can explain as another about your energy band diagram. This is the conduction band, and this is nothing but your valence band. If the electron they move towards here, if the electron in the valence band they move towards the conduction band, then what happens? If the energy is lost by this free electron, then once again they come back towards the valence band. If energy not sufficient for the electron, then what happens? It is once again come back to the valence band, then they will merge, they will recombine the whole. That also one type of recombination. No doubt you are applying some energy because the energy, the valence electron they move towards the conduction band. If energy not sufficient, then what happens? This electron once again come back and they meet, they will recombine with the whole. This recombination nothing but they will disappear, they will neutralize, they will give the energy. Because that energy once again break a covalent bond is so important process in the, it happens in the semiconductor. This is nothing but the recombination of the electron hole. This is about the basic knowledge. We will look for the most important thing about the extrinsic semiconductor. We will look for the most important thing, the extrinsic semiconductor. Extrinsic semiconductor. We will go importance of the extrinsic semiconductor. Here, as I said already, in intrinsic semiconductor, they are called pure, 100% pure. The semiconductor is in the purest form. That is something about your intrinsic semiconductor. And extrinsic nothing but they are called impure. They are called doped semiconductor. And the materials which are impure, they are another way of there is nothing but doped semiconductor. What are the extrinsic semiconductor? The extrinsic semiconductor or the semiconductor, they are in the impure form. They are not pure. Also, they are adding the impurities to a pure semiconductor. That is nothing but extrinsic. It is also called as doped semiconductor. It is also called as doped semiconductor. Doped semiconductor. Or it is also called as impure semiconductor. Impure semiconductor. It is also called as impure semiconductor. It means it is also called as impure semiconductor. It is also called as doped semiconductor. It means the extrinsic semiconductor nothing but impure semiconductor, or it is also called as doped semiconductor. Look here, as I said already, you are having some drawbacks and limitations of your intrinsic semiconductor. That's why while constructing the diode, transistor, or your rectifier, oscillator, will prefer the extrinsic semiconductor. Why we prefer extrinsic semiconductor? No doubt, here it does not act as the insulator for low temperature. Also, the conductivity very more. In the extrinsic semiconductor, the conductivity very more, and also important thing, the number of electron holes are not same. The number of electron holes are not same. These are the advantages of your extrinsic semiconductor. And extrinsic semiconductor, but the doped semiconductor or is called impure semiconductor. Maybe you are studying in chemistry. What is called doping? The doping nothing but adding the impurities. Adding the impurities to a pure semiconductor to increase the conductivity. That is nothing but doping. The doping nothing but adding the impurities. Adding the impurities. Adding the impurity to a pure semiconductor. That is nothing but doping. And on the basis of doping, you have done the two types of extrinsic semiconductor. On the basis of doping, you are studying about the two types of semiconductor. One is called your write about types of semiconductor, types of extrinsic semiconductor, types of extrinsic semiconductor, types of extrinsic semiconductor. Look here, you have done the two types of semiconductor, extrinsic semiconductor. The one is called the N-type semiconductor. One is called the N-type semiconductor. And second one is called P-type semiconductor. P-type semiconductor. It means, as I said already, Externals is nothing but they are called impure, they are called doped semiconductor. It means doping nothing but by adding impurities. And what type of input you are adding? You have done the types on the basis of doping, you have done the types of semiconductor, N-type semiconductor and P-type semiconductor. Actually, it's so important question for your exam. We'll go in detail about the construction of your N-type semiconductor, or to say the formation of N-type semiconductor and formation of P-type semiconductor. We'll go in detail about the, while drawing the crystal structure, you can identify, you can easily understand about the formation of P-type and N-type semiconductor. In general, N-type semiconductor, but you are adding impurities. It may be pentavalent or it may be the trivalent. You are adding the two types of impurity. It may be the pentavalent, or it may be the trivalent. You are adding these two types of impurities to a pure semiconductor. A pure semiconductor, by adding the pentavalent impurities, that becomes N-type semiconductor. And a pure semiconductor, by adding the trivalent impurities, that becomes the P-type semiconductor. Now we go for in detail about the N-type semiconductor and P-type semiconductor. First we go for the N-type semiconductor, the formation of N-type semiconductor. We go for it. We look for the formation of N-type semiconductor. We go for the formation of N-type semiconductor. The formation of N-type semiconductor. Look here, as I said already, what is the N-type semiconductor? N-type, nothing but a pure semiconductor, adding with pentavalent impurity. That is nothing but N-type semiconductor. N-type semiconductor nothing but a pure semiconductor adding with pentavalent impurities. It means what? As we know, the N-type, nothing but a pure semiconductor, it may be silicon or germanium, plus can add with them Si, you can add with them arsenic, As, or by adding the phosphorus, or arsenic. A pure silicon or germanium, by adding with the arsenic or phosphorus, that becomes the N-type semiconductor. A pure semiconductor, silicon or germanium, by adding with the arsenic or phosphorus, that becomes the N-type semiconductor. This is in general the definition of your N-type semiconductor. Now, if you draw the crystal structure, then you understand very easily about how you can formation of your N-type semiconductor. Can we talk about the crystal structure? By the crystal structure, we can identify the how actually we can form the N-type semiconductor. As you know already, in your pure semiconductor, they are having the tetravalent covalent bonded crystal structure. It means what? In your semiconductor, I have the 4 valence electron. In the semiconductor, you have the 4 valence electron, and we are adding the pentavalent impurity. It means they are having the 5 valence electron in the outer orbit. A pure semiconductor having the 4 valence electrons. You are adding with the pentavalent impurities. Pentavalent impurity, they are having the 5 valence electrons, and actually in the outer orbit, they are having only maximum 8 electrons. In the outer orbit, having the only maximum number of electrons are 8. But when you are adding the 5 valence electrons, then what happens? You see by the crystal structure. The crystal structure of N-type semiconductor. N-type semiconductor. Look here, then draw the crystal structure. You can draw the crystal structure and you can understand very easily about the by drawing the crystal structure. You can understand very easily about the formation of your semiconductor or PDA semiconductor. Yes, as I said, in the middle you are having the phosphorus and you are having the silicon surrounding all the, as I said, in your N-type neighborhood. A pure semiconductor is aluminum or silicon by adding with the pentavariants. It is nothing but your yes side. Now we are in the covalent bond. Covalent bond nothing but the sharing of valence electron from the neighboring atoms to become the stable state. Already discussed in the last class. What is covalent bond? The covalent bond nothing but the sharing of valence electron from the neighboring atoms to become the stable state. Look here, these are the covalent bond, and important thing, as we know already, in the valence electrons, in the bond, you are having the this is nothing but the crystal structure of your N-type semiconductor. As usual, you are having the electrons are there in the outermost orbit, and you are giving importance to outermost orbit because it is far away from the nucleus. It is far away from the nucleus, and important thing, if you apply very small energy, there will be come outside. Because the small energy will be come outside. This is know already. This is nothing but your crystal structure of your N-type semiconductor, and as usual, as I said here, we are adding the pentavalent, especially we are adding phosphorus with the pure semiconductor. And as we know, in the crystal, having so many atoms are there, they are very coolly spaced and systematically arranged. And look here, this is about the crystal structure of your P-type semiconductor. Now, actually, we know already. Yes, in the pentavalent, nothing but 1, 2, 3, 4, 5. We are in the 5 valence electron, the phosphorus. Because what is N-type semiconductor? A N-type semiconductor, nothing but a pure semiconductor by adding the pentavalent produce, especially by adding the phosphorus. Phosphorus having the 1, 2, 3, 4, 5. We are having the 4 valence electron. In the pentavalent, nothing but we are having the 4 valence electron. Actually, you are adding a pentavalent produce with a pure silicon thing. Then what happens? Look here, this pentavalent produce of phosphorus, they make the covalent bond with another core of our silicon semiconductor, a silicon material. In your pentavalent produce, the phosphorus having the 5 valence electrons. In that 5, the 4 of your phosphorus, they mix the covalent bond with another core of our silicon. That is nothing but make the covalent bond. As you know, to make it the stable state, to make it the octet, what they will do? They will take from the neighboring atoms, one electron from neighboring atoms. Then they will take here 1 electron, and they will take here 1 electron, they will take 1 electron, or they will take 1 electron. Or our phosphorus have 5 valence electron that make covalent bond with another core of your silicon. Then this is extra electron because we want 4 but it is having an extra electron. This is nothing but it is not having any covalent bond. It is totally free from the covalent bond, or it is totally free from the nucleus. This is nothing but your free electron. It is called free electron. Look here, why it is called free electron? Why it is called free electron? Why it is a free electron? Because it is totally free from the covalent bond and it is not also creating the hole. In anti-semiconductor, most important thing, it will create electrons but without creating the hole. As usual, you are studying in the inter-semiconductor. Whenever breaking the covalent bond, what will get? Will get the electron and hole come in place. But here, this electron come outside, but it is not. It will create a hole, and also it is not breaking the covalent bond. It means it is totally free from the covalent bond. It is totally free from the covalent bond. It means this electron is totally free from the nucleus. It is not having any covalent bond with the nucleus or remaining atoms. That's why this electron is nothing but the free electron. It means what I am saying here. Whenever we are adding the pentavalent impedance to a pure semiconductor, we get the more number of free electrons generated. We get the more number of free electrons generated. It means if we add a small amount of pentavalent impurities to a pure semiconductor, we get the more number of free electrons generated. We get the more number of free electrons generated. Keep it in mind without creating the hole. Without creating the hole, wherein the more number of electrons are created. It means whenever we are adding the pentavalent, a small amount of pentavalent impurities to a pure semiconductor, we will get the more number of electrons are generated. And keep it in mind, while adding the impurities, don't disturb the crystal structure. The crystal structure will be continuous. Like that, you add the very small amount of the impurities to a pure semiconductor. It means in your entire semiconductor, nothing but a pure semiconductor adding with the pentavalent impurities. And what I said here, no doubt in the pentavalent impurities we are having the 1, 2, 3, 4, 5 valence electrons. What they do, the 4 of the your pentavalent impurities, they will make covalent bond with the another core of our pure silicon level. The one electron that is totally free from the covalent bond, that will move very freely and they move towards the conduction band. It means whenever you are adding the pentavalent impurities, you will get the more number of electrons are generated. We get the more number of electrons are generated. Or you can create a more number of electrons and keep it in mind without creating the hole. Without creating the hole. And that's why the anti-semiconductor is also called as donors. They are also called as donors. The anti-semiconductor is also called as donors. Why they are called donors? Because they donate one electron to the conduction band. They are also called as donors. The anti-semiconductor is also called as donors because they donate one electron to the conduction band. That's why what happens in the anti-semiconductor, the majority carriers are electrons. The majority carriers are electrons. It means very simple. What you have to write in the exam? First you draw the crystal structure and the anti-semiconductor nothing but a pure semiconductor by adding the pentavalent impurities. It may be arsenic and phosphorus. Now we are adding the phosphorus. And as we know, the phosphorus having the 5 valence electrons, that 5 of valence electrons of your phosphorus, they make the covalent bond with another core of our pure semiconductor, silicon channel. It means one electron is totally free. It is not having any covalent bond with the remaining atoms. Because you want only 4, there are already 4. It is totally one extra electron. It is not having any covalent bond. This electron is totally free from the covalent bond. It can move very easily to move towards the conduction. It means whenever you are adding the pentavalent impurities to a pure semiconductor, you will get the more number of electrons are generated. That's why I said they are also called donors. They will donate one electron to the conduction band. This is about the importance of your n-type semiconductor. Another important thing, as I said here, whenever you are adding the pentavalent impurities, no doubt they will give an extra electron. and the added impurity, it means the phosphorus, if they may give one extra electron, that phosphor atom, that becomes the immovable ion, that becomes the positive immobile ion, that becomes the positive immobile ion. It means they are also called as positive donor ion, you can say that also. Positive immobile ion, it is also called as positive immobile ion. It means, as we know, the phosphorus, they give an extra electron. If the extra electron they may give, then that acts as a positive charge. The phosphorus atom, that acts as a positive charge, or that acts as a positive immobile ion. Why it is called immobile? Because it is not having any conduction process. It is not taking part in the conduction of the electron, conduction of current. The positive immobile ion, nothing but it is not having any current conduction because of the positive ions. It is totally bound to your nucleus. The current is not because of the immobile ions. It is totally bound to your nucleus. It means whenever you are adding the pentavalent impurity, the added impurity, that acts as a positive immobile ion. That acts as a positive immobile ions. Right? This is also an important thing about the positive immobile ion, because the electron come outside, the atom becomes positive, and that atom nothing but the you call as positive immobile ion. That is not having the current conduction piece. It is not you are not using the current conducting piece because of the positive immobile ions. The current is because of only electrons source, not because of this positive immobile ions. This is about the in simple way of your formation of n-type semiconductor. Now we will go for the LSD here. If we go for the energy band diagram, this is nothing but conduction band, and this is nothing but your valence band. Actually, another you are studying about the Fermi level, or it is also called as Fermi energy. What is the Fermi energy, or what is called Fermi level? Nothing but the Fermi energy, Fermi level, nothing but the maximum energy occupied by the electron in the absolute temperature or 0 Kelvin. What is Fermi energy or Fermi level, nothing but the maximum energy occupied by the electron in the absolute temperature or 0 Kelvin temperature. The maximum energy occupied by the electron in the absolute temperature or 0 Kelvin temperature, that is nothing but Fermi level or Fermi energy. The Fermi energy is nothing but the maximum energy occupied by the electron in the 0 Kelvin or absolute temperature, that is nothing but Fermi level or Fermi energy. Actually, in your n-type semiconductor, the Fermi level is very near to the conduction band, and yesterday here, this we are donating an electron. This electron is very near to the conduction. It can easily move towards the conduction band because that energy, if you go for this energy is very less. If you are in silicon, that energy is nothing but 0.05 volts, electron volts. But if you use germanium, that is nothing but 0.01 electron volt. It means here I am the Fermi level. Here I am your donors, who are having the free electrons. They can easily move towards the conduction band because they are having very less energy, 0.05 for silicon, 0.01 for the germanium. This energy can be given for externally, or the temperature is enough to move towards the conduction band. This is nothing but the Fermi level. The Fermi level is below the conduction band, and Fermi level nothing but the energy, maximum energy occupied by the electron in the absolute temperature or 0 Kelvin temperature. It is also called as the donor level. It is also called as donor level. The donor level is about 0.05 for the silicon and 0.0 for the germanium. It means very here. Where I have the free electrons are here. They can easily move towards the conduction band because their energy is about 0.05 and 0.01. This is about the n-type semiconductor. The important thing, the anti-semiconductor, what are the majority carriers and minority carriers? What are the majority carriers and minority carriers in the anti-semiconductor? In the anti-semiconductor, what are the majority carriers and minority carriers? Look here, this is your semiconductor. Sorry, this is your anti-semiconductor. This is nothing but your anti-semiconductor. In this anti-semiconductor, what I said, no doubt, the electrons are more. Why electrons are more? Because whenever adding the pentabolitis will generate the more number of electrons. It means the electrons are the majority carriers. Keep it in mind, the electrons are majority carriers. But the holes are minority carriers. No doubt you get the hole. That hole is because of the temperature, not because of the added impurity. As I said, in your anti-semiconductor, they will generate the electron but without creating the hole. That's why in the anti-semiconductor, the majority carriers are electrons. And also we are having some positive ions. They are having some positive ions. That added impurity that acts as the positive ion. As I said already, the added impurity that acts as the positive ion. It means here, you can write here majority carriers or electrons and minority carriers or holes. Keep it in mind, in the anti-semiconductor, the majority carriers are electrons and minority carriers are holes. It means what? Electrons are very more, right? Ne is more than Nh. It means number of electrons are more than number of holes. The number of electrons are more than the number of holes. It means in the anti-semiconductor, you look here and the more number of electrons because electrons are majority carriers and holes are the minority carriers. And how will you get the holes? That is because of temperature. The hole will generate because of the while breaking covalent bond, and you get whenever you break the covalent bond, we know already the electron and hole will come in pairs. This is about what are the majority carriers and minority carriers in anti-semiconductor. No doubt, in the anti-semiconductor, the electron majority carriers, it means electron very more, but holes are very less as compared to electron. But also we are having the positive ions. Why they are the positive ions? Because they will give one electron that added impurity, phosphorus or arsen, that acts as a positive ion. And here, why it is called anti-semiconductor? Why it is called anti-semiconductor? Why it is called anti-semiconductor? Why they are not given other names? Why only they are given the name anti-semiconductor? Because we know here, what I said here electrons are majority carriers. No doubt in the anti-semiconductor, electrons are majority carriers. And what is the charge of electron? The charge of electron is negative. Negative charge of an electron. Why it is called anti-semiconductor? Because here the majority carries electrons and electrons have a negative charge. This is N nothing but this is the N. N stands for negative. Because in anti-semiconductor the electrons are majority carriers. In anti-semiconductor the electron majority carriers and they are having the negative charge. That's why they given the name anti-semiconductor. No doubt in anti-semiconductor majority carries electrons. They are having the negative charge and that's why they given anti-semiconductor. Anti-semiconductor majority carries electrons. They are having negative charge. They are nothing but anti-semiconductor. They are nothing but negative charge of the electron. This is about the importance about your anti-semiconductor. And important thing, don't confuse here your anti-semiconductor is electrically neutral. The anti-semiconductor is electrically neutral. But how it is electrically neutral? Nothing but because we are adding the neutral atom to the, we are adding the neutral phosphorus to the pure silicon or germanium. That is nothing but it is called electrically neutral. This is about the importance about your entire semiconductor, and maybe you follow about the entire semiconductor. In the next class, I will for the P-type semiconductor. Thank you.